this place for atomic physics and other physics. She got her undergraduate degree at University College Cork and her PhD at the University of California, Berkeley. And she subsequently arrived at University of Colorado Boulder through positions at University of Michigan and Washington State. Her research is very, very broad. It spans AMO, nanoscience, laser technology, materials and chemical dynamics, plasma physics, imaging science. And the reason that is the techniques she's developing are broadly applicable to many, many areas. She's developed techniques where you can convert laser light into coherent X-rays in the UV and soft X-ray range, which is basically replacing a synchrotron with a tabletop setup. So it's something that had a huge impact on physics and material science and many other areas. She has many, many awards. She won the MacArthur Fellowship in 2000, and the number of awards is actually a whole page, so I'm not going to list all these awards. I just want to say we're very glad you're here and to tell us about higher harmonic generation and what you can do with that.
Thank you so much, Andy, and thank you for everyone, the students and faculty who I met today. It's really been a delight to visit. You have gorgeous, gorgeous environment and facilities here, and it's really a pleasure to visit. So thanks for the invitation. And as Andy said, I'd like to tell you about what we do in our group in generating laser-like beams at short wavelengths, and what we do with them. Everything in our group we do as part of a team. Henry Captain and I were a long time ago in the 80s, graduate students. We ended up being the first two students in a research group back when we were at Berkeley, and we solved the two-body problem by starting a joint group. And so all my work is done with Henry, and the more senior folks in the room will understand this, that the one thing you get when you do science with your spouse is you get very honest criticism, which can be hard initially, but as you get older you realize it is so valuable and it makes one a better scientist, because you cannot cover up anything, you're found out immediately if you and we're also just have just a terrific set of grad students and postdocs, and I'll mention their names as I talk about their work, and also a really terrific set of collaborators, and we hope from Kiel and Uppsala and NIST, and given your gorgeous quantum material facilities here, we'd love to collaborate with the groups here at NYU also. Okay, so some of the challenges we're trying to address, and I know you're very familiar with these here at NYU, is that if you look at the use of visible lasers, let's say to make the chips in your cell phones and your computers, much of that is the characterization is done with visible lasers. And in, say, mechanical engineering, as people are trying to understand heat transport and such at the nanoscale, those measurements are also done essentially with visible lasers. You can detect the light scattered from very small structures, and you can actually figure out whether there's a defect there or what the transport properties are if you have a good model. And the issue is that it turns out that there's a lot you miss at dimensions less than 100 nanometers, because if you can't see what's new, you can't change your model, and so you just have you don't have a very good loop. And so we're seeing that in many different areas, and that's only going to get harder as we try to do new kinds of energy efficient quantum technologies, spintronic technologies. Think about quantum. The surfaces and interfaces are going to become even more important than they are now, and it's no good to measure the static properties only. You also need to think about correlations and topology, quantum states. In many cases we know how to do this, in many cases we don't. And then if you think about something that the chemists dreamed of from the early days of the laser, So how would you, control a chemical reaction with light? And we all thought that was crazy enough, but it turns out we're beginning to see pathways. It sounded even more ludicrous to think about doing this with a material, but actually, as people are beginning to understand the interaction of light with materials, it's not as crazy anymore to think about transforming a material with light. And of course, this is very important because if you can't see or measure a material, you have no hope of understanding it, optimizing it, or manipulating it. And so what we do in our group then is just try to make new ways of doing non-destructive functional spectroscopies. And this is no different from, as Andy was saying, all the really gorgeous work that's going on at synchrotrons and X-ray free electron lasers. So in one way you could think, for those of you who have, who might have a background with lasers, you can think of the X-ray free electron lasers as the excimer lasers in the X-ray region, and you can think about the technology we're developing as the laser pointers. So we can do, metrology. We won't print a chip, but we can see if you've printed the right thing. So we're the metrology part. And so, for why have people invested huge amounts of funds in developing the current generation synchrotron sources and the next generation X-ray free electron laser sources? Is that you can do things with short wavelength light that you can't do with visible light. You can penetrate multiple layers through visibly opaque materials. You have these beautiful chemical and magnetic and spin specificity. There's characteristic absorption edges. You know what you're looking at, what its oxidation or magnetic state is. And so that's really nice. But there's a few more things we can do now that you can't do with current generation synchrotrons. And that is that if the light is coherent, then you can compress it in space and time. And so what that gives you then is you can make very high resolution images that are limited only by the wavelength of the light, and you can make very fast pulses to whatever bandwidth Fourier transform or Heisenberg uncertainty principle that you can have a coherent light. And then this is can be non-destructive because of course we'll never, or I won't say ever, but it's hard to compete with the gorgeous resolution images you can get from an electron microscope. But you have to cut a little piece out of the material to put that sample into the electron microscope. With X-rays you can do a non-destructive imaging, so it's very interesting, especially for functional systems. They have advantages. So why not make X-ray lasers? We've had visible lasers now for almost 60 years. We were so excited, our field, that last year the Nobel Prize in Physics went to ultrafast lasers. But if you look at the history of lasers, it's very surprising. So when Neyman demonstrated the first laser, people didn't really know what they were going to do with a directed beam of light. In fact, it was called a solution looking for a problem. They just had no idea that it would power the internet and you do BEC and there's cooling and all of this. But what's, when you think about, it powers the internet and all of this, you would think, and with the Nobel Prize, you would think laser science is a very rapidly moving field. Actually, if you talk about the wavelength, it hasn't been. In fact, the first ruby laser had a wavelength just under 700 nanometers. And the shortest wavelength laser that's in widespread use is the excimer laser at 193 nanometers. That prints most of your chips in your phones and your devices. But that means that in almost 60 years, the wavelength of lasers has decreased by a whopping less than a factor of 4. So it's actually quite remarkable because in data storage or computing or in every other area of imaging, the progress has been like many, many orders of magnitude. And so that's why the technology we're developing is interesting as a complement to the free electron laser sources because it is the only way to get to a coherent light. It's the only tabletop way to get to tunable coherent light below the ultraviolet region of the spectrum. So, but why not? Why was it so hard to make X-ray lasers? So the reason is that if you want to make an X-ray laser, you better put atoms into a highly excited state. And things in highly excited state do not have a very long lifetime. They want to decay almost immediately. In fact, you can use the Einstein spontaneous and stimulated emission coefficients to do a little back of the envelope calculation that tells you how much power you need to make a laser at any particular wavelength. And that is a very, very brutal scaling law, because what it says is that I can hold a laser pointer in my hand because I can power it off a battery, but if I want to make a 1 nanometer laser based on population inversion, I need a terawatt of power. That is about the electrical generating capacity of the United States. So nobody is going to make a continuous wave X-ray laser. It's just not possible. And then if you go to an angstrom, it's even like more mind-boggling. And that's why the first laser-like X-ray beams were not based on population inversion, but based on accelerator technology. So this is why the X-ray free electron lasers are being built. This is just for the folks who remember the Reagan Star Wars era. The proposal there was to make an X-ray laser to shoot down a missile by detonating a nuclear weapon in space. But that's not scalable, right? And so that's why this is the electron accelerator near the freeway interchange at the SLAC lab at Stanford. There's a 2-kilometer long accelerator, and then a series of magnets wriggles the electrons, and under the right conditions that the emitted X-ray light is laser-like. And this came online lasing at 1.5 nanometers in 2009, just about the 50-year anniversary of the laser. And Steve Chu was Secretary of Energy at the time, and of course Steve has a very good wit, so Steve at the Laser Fest celebration said, "Oh, these are marvelous machines, and they can do marvelous things, but the one thing they're not is free." And I should know it. Because it turns out that the first version of the LCLS-1 is $1 billion. And then with the additions, it's going to be, creeping up to $2 billion. So it's marvelous, and of course used by many scientists. But it is also worthwhile seeing what we can do on a tabletop, so we can, see about, what applications we can pursue. And so essentially, what I'm going to try and show you is that just because of the physics of extreme nonlinear optics, we can actually get amazing control over X-ray light by using quantum mechanics, quantum physics to manipulate a radiating electron wave function. And I won't go into details now. I'll come back to this slide and see if I can show you, what amazing quantum physics can do. Okay, so the light source that we are using is based on a high-order harmonic generation process. So it's the extreme version of the laser I'm holding in my hand, an infrared laser with that second harmonic crystal to add 2 infrared photons together to give green light. Now it turns out that in an accidental discovery in Charlie Rhodes's group in Chicago that was funded by Star Wars, so it was very interesting. Back in 1987, they discovered what Henry likes to talk about, one of the more recent new things we learned about the hydrogen atom, because it turns out that all atoms and molecules, if you expose them to an intense femtosecond laser beam, it is very easy with a very modest amount of energy to have an electric field associated with that light pulse that depresses the Coulomb barrier that binds the electron to the ion. And so the atom can undergo tunnel ionization apart of the electron wave function. And that part of the wave function is then free in a very intense light field. It will move away and return in this boomerang path, because of course the light field is oscillating, and convert the wriggle energy of motion to a coherent X-ray. And this is happening on every half cycle of the laser field. So that gives you a periodic emission in time, and of course we can all do a Fourier transform in our head. Periodic emission in time gives you periodic emission in frequency. And so this is this process of harmonic generation. I was talking with the students earlier and said I like the analogy with sound, that if you pluck a guitar string gently, you'll hear the fundamental tone. If you pluck hard, you will hear the harmonics, and if you pluck really hard, you break the string. A femtosecond laser, it turns out, breaks the quantum atom. It doesn't matter. The X-rays have already come out by the time you've broken it. So it's sort of a really nice, they're just perfect for perturbing the electron initially starting out in the ground state. Carlos Hernandez Garcia made us a little quantum movie. So think about this as a 2D representation of the electron in the ground state of hydrogen. And this is what's happening, the electron wave function, as it's being driven by a femtosecond laser pulse. You can see it's undergoing tunnel ionization, and these high frequency spatial modulations on the wave function. Think about, we've got to use Jackson, we calculate the time-dependent dipole moment, and then we square it to figure out the acceleration and the radiated field. So these high-frequency spatial modulations on the wave function look as if you're driving that electron at much higher frequencies. So essentially there's a beautiful, you can think about it as a nanoscale quantum antenna. And everything I told you was understood by the early 1990s. And what took us almost another 20 years was to figure out how to make a good beam of light, because the emission from each atom is a dipole field, which is not directed. To make a beam, what we had to figure out something that for optics folks might seem very simple, which is how do you combine the emission from many atoms in the medium in phase, and if you do that, you will get a beam in the forward direction, just like, you know, the difference between a light bulb and a laser is coherent emission. And part of the reason it took so long is that the atomic physicists were going to DAMOP, and they knew this part, and the laser scientists were going to the Division of Laser Science meeting, and they knew this part. And it took 10 years to sort of bridge the language gap, and so then over time then we all figured out how to do it. And I should say it's, you know, I'm sort of being a little bit flippant here. It's actually, it's not easy to do. And Carlos made us this little cartoon to sort of show that we were done, but, you know, you could explain. So you can think about the laser field as a quantum conductor trying to get the same number of atoms as there are people on Earth to sing in tune at the same time. Or in other words, to radiate in phase at the same time. The laser wavelength is 1 to 4 micron, but the harmonics we're making might have a wavelength of a nanometer, and that is a big difference. So that, you know, so that means, so in other words, if you want something to add in phase, you've got a certain wavelength. To what precision do you think you need to line up the different waves? Is it within a wavelength? Would that do it? No. So it has to be on order of maybe a 20th of a wavelength, so that all the crests would line up. A 20th of a wavelength at 1 nanometers is a sub-angstrom spatial. At 1 nanometer, a single cycle is about 2.5 attoseconds. So that means that you're trying to make all of the X-ray waves, you need to combine them with sub-angstrom and sub-attosecond temporal resolution. And we don't have any electronics that would allow one to do that. So there's the only thing the only thing you can do is figure out what the physics is, and then use that to, and so nature does it passively, and we're very fortunate that it works. One of the reasons it works is that tunnel ionization, which is what this is based on, is exponential to the 11th power in the laser field. So the electrons are all being released at a very particular time during the laser field. So it's very deterministic. So that's why a laser wavelength that's much longer than the X-rays can actually generate X-ray waves that are all synchronized. So we're very fortunate that the physics allows that. This is the only sort of graph that shows some equations that sort of shows that the idea, how we do it, is that X-rays traveling through anything, you know, they are not bent. They have a refractive index of 1 because they just go straight through objects, whereas laser light slows down in a neutral medium and to phase velocity less than the speed of light, and in a plasma it has a phase velocity greater than the speed of light. So on the leading edge of the laser pulse, the laser is traveling too slow compared with the X-rays, and on the trailing edge of the laser pulse, the laser is traveling faster than the X-rays, and as fortunately, for every color we've looked at, there's always a part of the laser beam that travels at the phase velocity given by the speed of light. And that's where we can do phase matching, and so we're very fortunate. You know, there's no law that said this had to happen, but the physics actually works out that way. And so we can draw sort of predictions and fill in that if we use this color laser, we can make these color X-rays. And so we have a recipe. It actually works better than this. Because this is just a simple one color experiment, but at least this sort of maps out where we can make light. And so practically what we do is we use different color lasers from the ultraviolet through the mid-infrared and near-infrared. We focus into a gas-filled waveguide, and then we get short wavelength beams that go from the vacuum ultraviolet to a nanometer now. And with reasonable conversion efficiency of about 10 to the minus 5, 10 to the minus 6. So if we use a 10 watt laser, we get microwatts of power in the EUV, and that's fine for spectroscopy and for imaging. I might skip this so I get to some materials applications, so let me
But it doesn't, the gas is just at room temperature, so it's...
The gas is just at room temperature,
Doesn't
that's
matter
right,
that
high
there's all
pressure
kinds
room
of-
temperature.
yeah, no thermal motion doesn't kill...
That's right, and the rep rates are and I apologize, I'm not able to, we can do all kinds of manipulation now. We can make beams that are circularly polarized, linearly polarized, elliptically polarized. We can impart orbital angular momentum, spin angular momentum on the beams. We can change the color of the driving laser and make an X-ray supercontinuum or a single peak. And so this is great for what we call a transient absorption or backlight measurement. And these are great for photoelectron spectroscopy measurements, for example. There's beautiful spatial coherence, and we can make these ridiculously short pulses, shorter than we thought we'd actually need to look at anything, but these just come out because of the physics. That you're only making harmonics while you're ionizing the atom and while it's phase matching. And it turns out those two things first shrink the emission to where it's shorter, far, far shorter than the laser pulse you're using to make it. And so this is just the physics. We don't get to, change that. We can be smart and manipulate it, but fundamentally, and so when I want to get my laser friends perturbed a bit, I give them a challenge and say, that I could have a good argument with you. I may not win it, but we have better control over light in the X-ray region than we have in the visible, only because in the visible, we use population inversion and perturbative nonlinear optics and then optics. Here, because you have a wave function that you can perturb with other light, we can actually control the X-ray emission with visible lasers. So it's actually better than optics because we can actually not, we're not limited by our ability to manufacture very good optics. So this usually gets them smiling. I mean, okay. And then when you add in a little bit of engineering, and this was, Henry realized that we were making things in our JILA labs that did fine for some applications, but they were not engineered, not like the beautiful systems I've seen in the Center for Quantum Matter, where you really take advantage of the fact that somebody has done the engineering to make it stable. So fortunately, Henry started a company, so we started then to go from our home-built systems to something that was more engineered, to where the stability is, and we've done better actually since, I just don't have the new data, but the stability is the same as synchrotrons and in some cases better and comparable to lasers now. And so that sort of lets us think about being the the complement to the beautiful synchrotron and X-ray free electron laser sources. And the way I like to say is that these are designed to do amazing experiments, where you need the high brightness, you sort of need the tunability and such. But the one thing the tabletop is great for is that the students can actually drive the innovation, because many of us know that that's where, that not all discoveries are planned. And sometimes it's the ability to notice something strange and then go back and take another sample and do some, iterative testing is where we can really, see when there's something new happen. And that's happened to us in every single material we've looked at. Our students have gone through that process, every single material. So these are the type of applications in materials we're pursuing. And this was sort of an interesting one. It was on a nanoscale hotspots. How did they cool? And the lore was that, if we think about in bulk cooling, if you want to cool something down, you're surrounded by a lot of cold material. And it was well known that if you had a nanoscale hotspot, it had a hard time connecting to the full phonon spectrum in the substrate, because if the size of the hotspot was smaller than the average phonon mean free path in your substrate, the heat transport would not be efficient. So our students did an experiment as we were exploring this, where they packed a whole lot of hotspots very close to each other, which is the opposite from what you would think intuitively, and they cooled faster. And so the first MRS meeting, I think it was in Boston, they presented this result at the engineers, the mechanical engineers all said, "This, you must be measuring it wrong. It can't possibly be like that." They went back, did their light scattering measurement, came back and said, "Okay, we agree, there's an effect there, but you must be interpreting it wrong." 3 years later, they came back and said, "Okay, yeah, there is." So what's happening is that if you think about it, when you pack hotspots very closely together, this looks like a thin film. So the inability to connect well to the phonon spectrum in your substrate, you fix it by just pack it. So it's a funny case where you can load a material with higher energy per unit area, and it still cools faster if you do it right. So it's the example of sort of the interesting new things you can learn by just having the ability to rapidly test. But I'd like to just tell you, probably in the time I've left, tell you about what new things we learned about magnetic materials. And if I, okay, and in fact, we developed a technique that, as somebody who's been in ultrafast science for a long time, that we should, our community should have figured it out sooner. We call it ultrafast electron calorimetry, and all it is that for those of you who do ultrafast, use ultrafast lasers, you know that if you shine a laser, let's say on a metal, the electrons will heat up very quickly because their heat capacity is less than that of the lattice, and then they'll undergo electron phonon scattering, the electrons will cool and the lattice heats up. And because the disparity in the heat capacities, you can heat the electrons to thousands of degrees Kelvin, while eventually when they cool down, the lattice might only be heated by 5 to 10 Kelvin, so you don't damage the material. What we found by falling over it in the lab is that if your material undergoes a phase transition while the electrons are cooling, because the coupling changes, you should see that phase transition written into the electron temperature. So that's why we call it an ultrafast electron calorimetry, that we get access to the electron heat capacity separate from the lattice heat capacity, because they're decoupled for a picosecond, which is on order of the time it takes for very hot electrons to undergo enough electron-phonon collisions that you can actually cool the electrons. And it turns out we've been looking at a few different materials using this approach, magnetic materials and charge density wave materials. And in both cases, we were able to find sort of some curious new behavior. In a whole range of magnetic materials, what we're seeing is that the ultrafast lasers can directly excite spins in very fast timescales. In fact, now this is, I forgot to update this. This is about maybe femtosecond to attoseconds now. And the reason it wasn't seen is not that it wasn't happening, but a lot of spectroscopies measure the average excitation in the band in a material, and so they average, and so if you have a high non-equilibrium excitation, you just can't see it with a traditional magneto-optic spectroscopy. And then similarly in these charge density wave materials, we think about tuning their properties with pressure or with doping normally. Turns out that if you use ultrafast light, it naturally interacts with the charge, and we're not the first to see that you can excite one of these breathing modes, that are related to the periodic lattice distortion in these charge density wave systems. But what we didn't realize is that here in 2D materials, ultrafast lasers have an advantage, because what they do is because the cross-plane phonon modes are very, very weakly coupled, for about a nanosecond, you've made the material more 2D-like, so you can actually explore the couplings in that 2D material and actually drive it into new phases. I probably won't have time to talk about it, but it just shows that there's a number of interesting things we can look at with ultrafast lasers.
Just a quick question.
Sure, of course.
How do you determine the electron temperature? Are you doing some spectroscopy?
Yes, and I will show you
you'll show
exactly.
that,
In
okay.
fact, it's very simple. We just take a line out of the Fermi edge. We do
Okay, so you look at the
photo
Fermi-
emission spectroscopy, take a line out, fit to a Fermi derive,
Mhm.
and we wait for, we do this about maybe 10 femtoseconds in, so that you've got enough electron-electron scattering
To
that
cool,
there
yep.
is a temperature
Mhm.
established.
I see. So you're using 3 kT edge there.
Correct. Correct. Exactly. So, so let me give an example of how we fell over this technique by looking at how fast one could switch a magnetic material. So for a very long time, people thought that the fastest dynamics in magnetic materials were associated with the precession of spins. So on picosecond to nanosecond time scale, and then about 22 years ago, when ultrafast lasers became usable by other people, Jean-Yves Bigot and Eric Beaurepaire did an experiment where they just shone a femtosecond laser on a magnetic material and saw that the magnetism quenched in an incredibly fast time scale. And so the question was, what's going on? So this was sort of the quandary, that you could make a really fast laser pulse. We can make 10 or 20 femtosecond laser pulses, no problem. But no matter what material, in that intervening time, no matter what material one would look at, you'd get a curve for the magnetic quenching that looked kind of like this. That it took about a half a picosecond for the magnetism to quench, and then it started recovering. For those of us who do ultra-fast science, this is a weird time scale, because it is far too slow to be associated with charge dynamics, which should happen in tens of femtoseconds time scale. And it was far too fast to be associated with lattice dynamics, which should take about a picosecond to heat up. So this always looked a bit, strange to folks, but but that was what the data showed. So people assumed that what must be happening is that you started with a magnetic material in a ferromagnetic state, and that this timescale must be associated with some spin flip scattering process to randomize the angular momentum. And so this was what was taking the time, and so there was a very nice model, like these T3 temperature model that assumed the electrons got hot very quickly, and then there was some electron phonon spin flip scattering that would heat up the spins, and then the lattice. And so it was a trickle down. So the light coupled to the electrons, that then randomized the magnetic order, then other processes such as thermal conduction and electron phonon coupling happened later, and there was certainly some theory that said that there should be faster processes, but nobody could see them. That was the problem. They didn't turn up in the experiments. So even though theory was predicting much faster response times, nobody could see. So what we've found is that using this ultrafast electron calorimetry, we see fast spin excitation in any material we've tried. That does not mean we haven't tried anywhere near enough to know that this is general, but that essentially we see it in simple ferromagnets, in alloys, Heusler alloys, that what we see is that the spin excitation happens instantaneously, or with the light excitation. But you make these exotic excited states that they're hard to see. And so, and then only when those exotic excited states relax, but the even though it's not the right analogy, but the latent heat from the laser goes in here. I know this is not, for those of you who, but it's just to get the idea across, and that it's this relaxation of a high energy magnon state to a low energy magnon state that is propagated throughout the band. This is what the magnetic spectroscopies see. So that's why people missed it. So,
a quick question.
Sure.
So are you saying that essentially the total spin moment, if it's a ferromagnet, the total spin moment is staying the same, but you're mixing up where?
Okay, so let me try and
creating
explain to the best of my understanding. Yeah. So and there is no theory on this right now, but this is what we think is happening, that you have very hot electrons, they have enough energy to flip a spin. When you do that, you conserve angular momentum because it's a high energy magnon, so you have made the spin flip, but you haven't dissipated the angular momentum. And so, but the interesting thing is that this happens during the laser pulse, and once that's made, the material will undergo a phase transition. So that you've launched the magnetic phase transition. So it's not that different, but it's just interesting, yeah. So it turns out high harmonics are very interesting to probe magnetic material. So this is a little spectrum of the high harmonics, and at the M shell absorption edges, they span nickel, cobalt, iron, manganese, ruthenium, and they're very nice. We have this, we can shine this on an alloy or a multilayer, and so we can probe the magnetic state of each element in the alloy or each layer in the multilayer. And that's what is nice. You can't do with other techniques, and we have very high time resolution. And so you can think about this as either the shorter wavelength version of visible MOC or the longer wavelength version of soft X-ray out-of-shell spectroscopies. But we started to get some hints that when we applied the regular spectroscopies, that we weren't actually seeing what was going on in the material. So we started a campaign where we started doing multiple spectroscopies on the same sample. And it is very easy with the same high harmonic source to implement time-resolved RPs and time-resolved magneto-optic spectroscopies, they probe very different things about the sample. With angle resolved photo emission, that you have the beautiful setups here. You're looking at the surface. You can. This is what we can measure. For example, the electron temperature by taking a line out at the Fermi edge, and we fit to different temperatures. We can measure the exchange splitting when we can see them, and that is at the surface. And then with the magneto-optic curve spectroscopies, we measure the bulk magnetic order, and we can actually measure the on-resonance electron reflectivity and extract the electron temperature. So we have two ways of seeing that we're measuring the right electron temperature using two very different techniques. So initially this was done as just a survey. Do we know what we're measuring? It was just done as on nickel, we didn't expect to see anything new. And we were very happy that the demagnetization curves I showed you earlier, they looked the same with the both spectroscopies. That was nice because we didn't know that was going to be true. But then we started looking at the photo emission data more carefully. And so what we did was plot the electron temperature by looking at the Fermi edge as a function of laser fluence. So that's what's plotted here. So we take our piece data, do that in a pump probe manner, and fit the electron temperature at every time delay, and then do all of that as a function of laser fluence. And then we plot the electron temperature as a function of laser fluence, and what we expected was to get the purple line, that if you've got a typical electron heat capacity in a metal, you'll have a certain heat capacity. As you pump more laser energy in, you should heat the electrons. But you don't see that. You see that it gets harder and harder to heat the electrons as their temperature approaches the Curie temperature. And this is the temperature measured 24 femtoseconds, into the laser pulse. And then once you get above the Curie temperature, it's easier to heat. So this yellow is the energy being pumped into the spin system. And it turns out that if you actually, I don't have it here, okay, that you can extract essentially the electron spin heat capacity. It's got a critical behavior. So essentially, and we can also correlate that with the exchange splitting. And what we see is if we heat gently so that we stay below the Curie temperature, the exchange splitting collapses initially but then recovers very quickly. But if we heat the electrons above the Curie temperature, the exchange splitting collapses and stays collapsed, indicative of a magnetic phase transition. And it connects this ultrafast phase transition to the equilibrium behavior, because essentially this is sort of the same result you would get if you heated up the magnet on a hot plate. So
with the magneto-optics, there's still a magnetization, right? Even though the magnetization is decayed, there's still magnetization. Is that the right
there's
picture?
no complete theory, and I'll try and show you the cartoon, but the whole idea is that the energy is transferred to the spins during the laser pulse. And then and so essentially this is what we think is going on. So but there is no theory, although Martin Weinelt, who's from Berlin, he had a theory paper where he proposed that of course they should happen, because if you look at electron-electron exchange scattering, that can happen very quickly. Electron-electron scattering is sub-femtosecond, and they can flip a spin in few femtoseconds, if there are a few eV above the Fermi level. So that this is actually, except that there's no complete theory, but so in other words, we're not we're not violating sort of any physical, And so the idea is, if you heat it gently, you heat the electrons, there's some above the Fermi level. One of these electrons can, the hot electrons can then undergo a transition from above the Fermi level to the minority band, because you pump some out of the minority band to below the Fermi level, and that will give you a spin flip. But if you only have a small number of spin flips, because you didn't really heat very strongly, that material can recover very quickly, and so it's just, you haven't really driven a magnetic phase transition. But if you heat more strongly, then there's a lot of electrons above the Fermi level. You can have a lot of spin flips, and now this is sort of a high energy magnon state. You don't have that many, but then as these relax, then you have a high density of low energy magnons. This would be the state you would make by normally heating the magnet. And of course, it is nice that it is, it shows that the out of equilibrium behavior is, not, you would never make this state, of course, by just direct heating, but these relaxes to something, to a similar state. And then we thought, well, okay, so, this idea of having, with the laser, heating electrons well above the Fermi level, and then having some relaxations to make magnons, that would be very different in one of these Heusler half metals, because some of these scattering channels would be blocked. So what we all thought going into this is that all these blocked channels would mean that we wouldn't be able to manipulate the polarization in the Heusler metal very fast. So we all expected this to be a much slower loss of magnetic order. Until we did the experiment, and it turns out it was like, it was even faster, that essentially immediately when we shone the laser light onto this Heusler alloy of cobalt, manganese, germanium, the magnetization in the cobalt went up, and in the manganese went down. So in this alloy, you get some transfer of spin polarization from the cobalt to the manganese, and then after you shine light on it, you get a transfer back extremely fast. So it was the opposite of what we were expected. These are hard signals, so we hadn't been trying continuously since 2010, but about every 2 years we would try the experiment, but the signal is very weak, so it took us a while to get it. And so, okay, so what's going on? So with our collaborators, Ole Eriksson's group from Uppsala, Ole calculated essentially that what we're doing is that if you integrate over all the transition, okay, so essentially it is more likely to excite a minority spin in cobalt and a majority spin in manganese. And so essentially that means that the light is effectively transferring the spin polarization. If you integrate over all possible transition probabilities, and this is the laser photon energy we're using, that it's easier to excite the minority band in cobalt, majority band in manganese, and that essentially takes spin polarization and takes it from the manganese to the cobalt. And if you measured the same material using visible light, because it averages between the two, you would get the black line. So it would just look like the normal demagnetization process that is going on in other materials, but now we know that it's just not that simple. So it turns out that we've looked at a number of different materials, and through our collaborators also, and essentially in all these materials we see much faster spin manipulation than we understood before. This is the spin flip scattering that we think underlies the nickel work, that essentially exchange scattering can happen, and we've measured that using other techniques. We've measured not the exchange but the spin conserving scattering process, and it does indeed, depending on the electron energy, can be super fast. This is the direct light-induced spin transfer that's going on in the Heuslers, and then there was other work that was proposed by our collaborator Peter Openier, and we confirmed and other people confirmed that essentially all these, there are very fast spin dynamics happening, but they're just hard to see. Okay, so I should double check how much time I have left. So should I stop here and give time for questions?
Speak for a few more minutes.
Few more minutes?
Yeah.
Okay,
5 more
so I'll
minutes.
talk about this charge density wave system only because I think and it's a selenide system, so it might be something we could actually collaborate on
Mhm.
from what I know that you can make on the MBE. And so this is a tantalum diselenide 1T that normally would either be in an insulating or metallic phase. And you know from the order parameter by the band shift that it shifts up by almost 0.2 in EV when you heat the material or if you shine an ultrafast laser pulse on the material. So we did the experiment. We take the material in its insulating state, and then heat it very gently with the laser, and you get the band shift, so you almost melt it, and then there's a ringing because you've excited the breathing mode, but it recovers very quickly. Then if you heat it very strongly, you melt the order. Oops. Just what's shown here. So now it's gone to the metallic phase and the band gap is closed and the band is shifted. But if you heated it at an intermediate fluence, it went back halfway in between the insulator and the metal and stayed there for a long time. So that's not enough for me to claim that's a new phase or anything, but what you can do is measure the electron temperature. So if you measure the electron temperature, what you start to see is normally the slope of the electron temperature versus laser fluence is related to the heat capacity. And what one sees is that a particular laser fluence, the slope changes. And there's even a jump, and by 4 picoseconds, there's actually a very big jump. And it turns out that jump is big enough that the effective heat capacity must be reducing to 1/3 that of the normal. All that's happening, it's a 2D material. We're not exciting the cross-plane phonons. So that's what's giving rise to that aspect. Or very likely, there isn't a theory, but we think that's what's giving rise. We think it's a new charge density wave state because we can look at the band gap at each point, and sure enough, this band gap is sort of half this. This was one of our first experiments, and we've improved our energy resolution since. So we actually, so what we think it is that we start in the charge density wave state, then very barely transiently melt, but this is a very distorted breathing mode because it's driven, quite in an unusual way that you could, and then that it relaxes back to a new CDW phase that's very likely mediated by the fact that you've lost all the cross-plane phonons. So this is our cartoon for that. Again, uninformed by theory, but we were just giving this idea that there's several phonon baths in the materials. So clearly, and it turns out, and I don't have time to show you, but the damping changes. You can sort of see that in the data depending on what you're exciting. And so the only way we can explain it is if there's strongly coupled phonons and other phonons, and we're interacting much more with the strongly coupled phonons, and then the other phonons heat up over time. And I'm not doing a great job of explaining it because I wanted to show just one more piece of data that's not even submitted for publication, but we'd love to explore in other materials, is normally when we think about heating a material with an ultrafast laser, you expect the electrons to heat up and then to monotonically cool. This shows that the electrons heat up, but then their temperature oscillates and is in phase with the breathing mode of the CDW wave. And if we do it at high fluence in this metastable state, there's a phase shift. And these temperature oscillations are quite large. They're by 200 Kelvin and up to 1,000 Kelvin in these different phases. So there really is a very, very strong coherent coupling between the electron bath and different phonon baths. And in this material, we think actually there's just many, even though we can't confirm this without a Rix measurement or something, which is why I'm trying to mention it, we think that, you know, at weak excitation, the coherent amplitude mode decays by anharmonic decay, and then that couples to the electrons, whereas at strong excitation, in this metastable state, the coherent amplitude mode is relaxing by modulation of the electron temperature. There's all of these other phonon modes also involved, so it would be a really neat experiment to see if we could, you know, this is what we think the RP's data is telling us, but it has to be tested because there is no. Okay, so in other words, the 2 temperature model for CDW materials and the 3 temperature model for magnetic materials you have to take them with a grain of salt for these strongly coupled materials. And with that, I'm going to go to my concluding slide, and I'll have to get out of display mode to do that efficiently. Just conclude, this is just for the graduate students because we all did our PhD once, that you know, this technology, you know, took a long time to get it to where it was it could be useful. You know, the NMR is a great example. You know, that the first versions, you know, I'm sure you've seen, I know this was at Berkeley, you know, so I think many of us have seen this, that, you know, there's a special circuit in the machine called the crisis detector that senses the operator's emotional state in terms of how desperate he or she is to use the machine. The crisis detector then creates a malfunction proportional to the desperation of the operator, and correcting the machine only aggravates the situation. And so keep cool and say nice things to the machine, nothing else seems to work. And you know, I think in experiment and theory, the code or the machine won't, you know, it won't work, and just about you're about to throw it out the window or something, you know, then the PhD experiment works. So so for the students, hang in there, and I hope I've you know, given you a flavor that, you know, these harmonic sources, they're very interesting, you know, quantum light source technology. We've really, you know, everything scales with the wavelengths, so as we go to shorter wavelengths, it opens up new measurement capabilities in imaging and other areas of science. And of course, the students who, there are many people who are responsible for doing this work over the last 15 years or so. So with that, I'd like to thank you very much for your attention.
Thank you very much for a very interesting talk. Are there questions?
If you have elements with large spin orbit coupling, and does it hasten the change in the sort of total magnetization, or in these, does it hasten the mixing up of the magnetic ordering?
We've mostly looked at you've seen almost everything we've done. I mean, we've looked at multi-layers, which so there are experiments that were done at the Bessie and the Daisy, you know, slicing beam lines. There, the jitter between the laser and the X-ray pulse meant that you know, they probably couldn't tell. Yeah. So I think so there's been a lot of so many I mean, so far you can only see the very fast dynamics with RPs, and so or a element resolved MOC. So I'm waffling because I'm just trying to think, has there been, so I think all the other experiments done on on other materials have not seen as fast a dynamic. Yeah. Although now people are, now that they know to look for it, there are at least 4 groups in Germany who I think are agreeing with us that there is very fast spin excitation. I wasn't at the most recent German condensed matter meeting, so I don't know what that new work is, but there's several people who are now doing spectroscopies that can, so, but I don't know what range of materials they've looked at.
Go ahead.
You're probably also creating spatial inhomogeneity,
Yes,
the domain
al-
walls and also that will slow
almost
down all those
for
things.
sure.
Is there any chance of probing these spatial
Absolutely,
inhomogeneities?
absolutely. I didn't talk about imaging, so we're doing the same types of coherent imaging that are being implemented now on the NSLS2 and such. And so looking at spatial inhomogeneities, we actually see it in the data, that there's a region between when we reach the normal Curie temperature and somewhat higher temperature where very likely there's some inhomogeneities present. Whether they're got to do with just the material being different, just because of, in many of the magnetic materials we don't have single crystal samples if we're doing MOC, so then there's a lot more ability for inhomogeneities to influence the actual behavior of the material.
Just a quick one. Probably you already said that, but in the magnetic systems, is there a state which cannot be interpreted as just magnons, excited magnons or it always can be interpreted like that? I'm talking. You are in the low energy state. You shine light laser and then you excite them, and the question is whether I'm just seeing the gas of magnons or this is a new state of matter.
I would. That's probably about my pay grade. I mean, so, okay. Martin Wiener thinks it is just this. This you have enough energy to do the spin flip.
For sure.
And it conserves the angular momentum because you just because you made a magnon.
For sure. But can I still describe that as a collection of excited magnons over the ground state?
Nobody. So we, this is just published, so I don't think anybody has actually. Okay. Yeah. So nobody has. So the fact that it's energetically allowed, like, thank God it conserves energy and angular momentum. So let's let's at least make sure. But there isn't any. There's no theory on that part. On the light-induced spin transfer, there's a simple, just calculating the optical transition, and then Sangeeta Sharma did DFT to to also do the same thing, and so she predicted that you should be able to do this direct light-induced spin transfer in these Heusler materials. So there's a little bit of theory, but I would say it's very early days on the theory yet. So exactly, I mean, this is why we have a lot of cartoons in our, because it needs more experimental probes, to add in Ricks and other things, and then a lot more theory. Yeah.
There's very interesting ideas also that you develop. If you have this gas of magnons, they develop inhomogeneities like droplets, which
yes. Well,
Dan
Tom does
Stein and I have
believe.
been
Yeah.
working on.
So I see. Yes.
Yes, we can
Tom
talk about
wants
that.
Tom definitely wants to
Because
see.
they interact with each other at these high concentrations, and they can attract. Yeah, they have collapse.
I think I had a question that was along those lines, but very naive, which is from someone totally outside the field. What kind of collaboration might happen? You mentioned a couple of times collaborating with people.
We are totally limited by materials, so we do not make materials ourselves. So we are totally limited by, particularly for the art piece work, it has to be single crystal and on the right substrate, so it cools, because you don't want you have to be careful that it doesn't. You're not, especially in the magnetic system, that you're just not heating it up by repetitively hitting it with the ultrafast laser. So we are just really, really happy to look at all kinds of materials and see, are these general findings or not? We don't know because they're so it's so, early days.
Thank you very much for that very interesting.